So the idea for today is to talk a bit about soft theorems and how to use them to deduce properties of gravitational waves in low frequency regimes, so soft spectra. Particularly, we will discuss the energy emission spectrum and the contribution to the angular momentum loss that come from low frequency, or more precisely from zero frequency mode, and so static mode or zero frequency. Okay, so of course the starting point is the soft theorem, and let me start by briefly reviewing. I mean, this is I'm sure very well known, but just to fix ideas, the statement is that we start from an S matrix element for a generic process, alpha going to beta. Let me now specify what those are. And the idea is that if we now dress this process, so alpha beta. Now, if we dress this process by, say, the emission, similar consideration also hold for the absorption of n of gravitons, with momenta k1, kn, so let me call this n, Sn, alpha beta, then to leading order in the limit in which these frequencies are the frequencies of these gravitons are very small, this admits a very simple form. It's just a factor in front. So a product actually of factor of each associated to a different graviton. Write down later times this amplitude here without any gravitons. Alpha beta. And here just introduce some notation. FJ for me is going to denote the contraction with the J polarization, so either say plus or minus or cross and plus polarizations of this structure here with three indices, capital F, which is just the root of h by g, or in my convention I might call this kappa sometimes, p the sum over all the states taking part in the alpha going to beta process, which we refer to as a hard process, PA mu divided by PA dot k. So more precisely, this F is a function of the hard momenta and of k, one of the soft graviton momenta. Then here let me introduce this subtlety that you see will play a role later. The original derivation of this statement goes back to Weinberg, 1964 in particular. There's a beautiful paper where he discusses both the soft photon case and the soft graviton case, and uses that also to deduce some no-Gauge results for higher spins, by the way. And in the original Weinberg approach, as well as many soft theorem approaches, which are based on S matrix elements, one cares about, so this more precisely, this hold in the limit in which each of these k is, say, a vector of this form, and omega is going to 0. So this is what we mean by soft limit. But one doesn't actually care what happens at omega equals to 0, right? Because if omega equals to 0 means, I mean, gravitons can be soft with respect to some scale, but they actually must propagate in some way, right? Instead, what we will do today is use a trick that includes also the behavior associated to zero frequency gravitons, or more precisely to the gravitational field, to the contribution to the gravitational field, which does not depend on the time at all. And to do this, it's going to be important to remember the I epsilon prescription that comes, as we will see in a second. I mean, is hinted at in a sense already by the Feynman one. So where does this come from? Just as an exercise, for instance, suppose you forget this formula, how can you rederive it? Well, you can use the Feynman rules that we actually wrote down on the blackboard a couple of lessons ago. So, for instance, you remember the generic process, and then focus on one of these legs. The key idea is that the soft graviton contributions that dominate, because they have this 1 over k, so 1 over omega whole in the soft limit, must all come from when the extra graviton line that we are adding is attached to an external leg. And the reason is that if we do so, say that this momentum is p, mu momenta are always outgoing, so this is q plus k. So what we are going to add, we are adding or multiplying by is, of course, the propagator and the vertex. So the vertex from minus I kappa and okay, let me write it down. Mu minus 3 minus k mu plus mu minus 3 minus k mu minus the mu p dot minus 3 minus k plus m squared. Let me write this in a new line, otherwise. Okay, times the amplitude without the extra graviton. And then you see, as long as we are focusing on k going to 0, we can actually neglect many of these contributions. For instance, this one, this one, this one. The whole contribution here is 0 because p squared plus m squared is 0. So here, from here, we just get a minus 2 p nu. And here we get another minus from minus I squared kappa. So this is indeed kappa p nu. So, and then from here we get p squared plus m squared is 0, 2p dot k squared is 0 because it's an on-shell external graviton. So you see 2p dot k, the 2 cancel, and the minus I0 stays, the minus I epsilon stays as we wrote there. Very good. So this was just a sort of reminder. Then this is for a single graviton. Who guarantees that when you have multiple gravitons, they just all factorize in the same way? This is actually an interesting exercise that I think is not in the 64 paper, but in the 65. And the key trick to see this is that you have to, well, of course, if you attach different graviton lines on different hard lines, they clearly factorize in the same way, simply because they appear with some P1 and P2 or P1 and PA. What happens when you add them to the same line? This is somehow the non-trivial bit. So we have P, K1, K2, I want to compare this with P, K2, K1. Then essentially what happens here is that from the first factor you get P dot K1, say. From the second propagator you get P dot K1 plus P2. I'm just writing the relevant bit of the rule over there, right? And from the other one you get the same thing but with P1 and P2 interchange, right? So now you see that when you sum up these two terms, you have to factor out together, and the numerator precisely cancels this extra factor, leaving out just the product. And then it's a nice combinatoric exercise to show that this holds for R are independent. Sorry, it's independent of the number of gravitons that you attach to the same leg. They just always factorize as P dot K1, P dot K2, P dot Kr. Very good. So the key physical idea behind this is that since these gravitons are very, very soft, they are independent in the sense that the process doesn't care. If you already emitted one, it's as if to the hard process nothing happened, and then you can attach another one in an independent way. Very good. So today essentially will be a lecture in which we will sort of try to play a dangerous game in which we almost work with amplitude, but not quite, because of that minus I epsilon prescription. We are also including a bit that is associated to the zero frequency or static Coulombic field. So for instance, let me adopt this decomposition, call this n mu. Usually we are used to working with amplitude which satisfy the word identity, right? The k mu, in this case, when contract with f mu is equal to 0. In a sense, this is true, but let's be a bit more careful about this step. Let me contract with n, and light there. So you have to factor out kappa, and then let me separate out the sum over the incoming and the sum over the outgoing state because they have different signs for this term, right? So let me see. When A is incoming, this guy is positive, so I can just bring it out. Instead, when the sign, when I'm signing over the final state, this is the negative, right? So PA dot n is negative. So when I bring it up, I have to flip the sign of the epsilon pursuit. And then I have to contract with the n sign. Okay. So now, of course, PA dot n cancels. Okay. And the last step is to, of course, remember momentum conservation, which is just sum over all the A's for the hard process equal to 0. So you can write, say, that sum over the out is minus the sum over the in. Okay. And then now you recognize this usual identity 1 over x. So using that, we should find 2y phi kappa sum over a nu delta of omega. And actually here there is a subtlety, namely the fact that this omega frequency is actually always positive, is such that we have to multiply this by an extra factor of 1/2. Otherwise we will always get a wrong result by factor of 1/2. So times 1. Like this point was already discussed precisely this way in a paper by Manuel Ridgway and Shen in 2022. The only way to make so the idea is that you are integrating. Okay, there is one issue, which is that normally the delta function you can think of it as an approximation of more and more sharply peaked Gaussians, and instead here the delta function is localized at 0, but only half of the Gaussian is bigger than 0. So somehow this is one issue. The other issue has to do. So one thing that we will do, for instance, is work with this representation, and then keep this I epsilon actually finite without sending it to 0. Right? Do all the calculation and then send it to 0, and then we will find that this is consistent with this other prescription. But it's a bit subtle and it's a bit unpleasant if I have to be completely honest. But this, what we are doing is just a trick. It's just a way of getting the right result, also including the static field by this amplitude-inspired method.
Carlo,
yeah.
K mu is not n mu times omega.
Yeah. So you see, here the issue is that omega times delta omega is 0 as a distribution. So this is an equality in the distributional sense. But I mean, this is very mathematical. What I'm simply saying is that you have to be careful how this appears in your calculation. If it appears like this, then you can indeed drop it. If it appears multiplied by 1 over omega, you can drop it. That's what I'm trying to say. Yeah.
You hear this, but so why in the second term it's omega plus I0?
Yeah, so you remember I'm working with this slightly annoying convention that for me all momenta are formally outgoing, But this doesn't mean that there is no distinction between the outgoing and the incoming ones. It just means that PA incoming is minus the physical momentum of an incoming particle. So in particular, it means that if you multiply a time-like past-directed vector times a null future-directed vector, you get something positive. Instead, if you multiply two future-directed vectors, you get something negative. So you have to be careful when factoring it out from, say, from here. What I'm writing is, of course, right? But then the sign of this quantity is positive in the case of incoming particles and negative in the case of incoming particles, outgoing particles. So when it multiplies minus I0, it will be minus I0 divided something negative, say, and then it must be plus I0 after. I0 is just a way you remember it is a small negative imaginary part. However, if I multiply and divide by something negative and I factor out something negative, it becomes a small positive imaginary part. Right. Very good. So this is a subtlety that will be important later on. But in particular, as we will see, it will only play a role in, for instance, in the gravitational field, it will play a role in fixing for us the time-independent part of the field, or say of the waveform. And it will not play any role in the energy, because the energy doesn't really care about the static contributions, also because they are localized at zero frequency, so they carry zero energy. Instead, it will also be important for the angular momentum. So what I want to do now is to rewrite this exponentiation in terms of an operator language. So the idea is to introduce some oscillator to satisfy the usual canonical commutation relations for harmonic oscillator. Let me also remind or introduce and remember some notation for the integral over the photons phase space. Notation. And the idea is that you can rewrite this exponentiation of independent soft factors using this operator. Delta hat is just an integral. Okay, and the star is going to mean for me that I'm also introducing a cutoff. Namely, I'm only integrating up to K0 that are at most some frequency omega star, which is going to mean the frequency below which this soft approximation holds. And then fj k times a Dagger and the fj, remember, are these f mu nu contracted with the polarization j polarization. So the sum of the polarization is left implicit, and the sense in which this object is useful in order to rewrite the soft theorem is that the following. So we define this quantity. So 0 is the state without any gravitons. S alpha beta is the S-matrix element for the hard process, so without any soft gravitons, and here is our delta hat. Then the original S-matrix element with the soft gravitons are simply given by, for instance, for the emitted gravitons by acting with the appropriate, say, annihilation operator on this S hat. This is just an identity, right? Because of course AJ will pick the coefficient of Fj, and the sign should be the of a dagger in such a way that it brings it to a factor which simply reproduces. So up to here is just a trivial rewriting, right? Now comes the step which is a bit new. So the idea is that now we want to use this statement about exponentiation in momentum space in order to go to impact parameter space. And of course, what we want to use is the iconal exponentiation that we discussed at length, in particular for the case in which this is a 2-to-2 process involving two massive objects that are in the classical limit. So we want to remember that in the Fourier transform, this eventually will just give the e to the 2I delta. And then there are two issues. So one issue is that Fourier transform of this, in this case is a 2-to-2, just give you the 2I delta. Then there are two points. So one is the fact that we are dividing out by this normalization, which is needed in order to reproduce the original formula. And for us today, this is going to mean that we are in particular subtracting the imaginary part from the 2-loop icon. How does this come about? So the issue is that if you calculate this explicitly using the Baker, Campbell, Hausdorff formula, right? We have the expectation value of an exponential of the sum of these two operators, and you want to rewrite it as the product of the two of the exponentials of the two operators. So what you will find is that this exactly subtracts the three-particle cut on one divided by e to the 2I delta hat subtract three-particle cut, or if you want the imaginary part to delta 2 from delta. And this is an exercise that you want I leave to you. It's very similar to the calculation we did at the end of the first lecture. Sorry, on the second lecture. And of course, what happens here is that since we are focusing on the soft contribution to this three-particle cut, it will only subtract the divergent part of the imaginary part of the 2-loop icon. But okay, when later on when we include not only the soft part of the 5-point amplitude, but the whole 5-point amplitude, I will be able to remove this divergent part off. So the first point essentially turns this into e to the I real part of 2 delta. And the second point is that this factor here is relatively complicated in principle. It involves this fj, which in turn involves p1, p2, p3, p4, this pa, and p1, p2, p3, p4 are related. Say for instance, p4 is minus p1 plus q, p2 is minus p2 minus q, right? And when you perform the Fourier transform, this Fourier transform is with respect to q. So we need to Fourier transform also this dependence that appears here. However, we can use our favorite argument, namely the fact that in the Fourier transform, the dependence on q just becomes minus I derivative with respect to b, right? If you bring it out, so you can use in particular the fact that this f it has a power series in q, so you can think of expanding it out in powers of q, transforming each order using this, and then you will end up with powers. Say, if you have 9 q's, you will end up with many iterations of this derivative acting on the iconal or real part. And now what happens? What can happen is that, of course, the first one will just bring down the derivative of the real part of delta 2, which is the impulse. We put even an index here. mu1 to n, same. And then when you act with the second one, okay, and then it will still multiply by the exponential, right? What happens with the second one is that you could act again on the exponent and then bring down another q, or you could act on q itself, right? But what only matters in the classical limit. In the classical limit, of course, it's convenient. It's enhanced. The contributions that come by always acting on the exponent are enhanced, right? Because you remember that this case like 1 over h bar. Instead, this, for instance, no longer scales with h bar, and so on and so forth. So what happens is that you will just generate q mu, q mu1, q mu n. So in practice, what I'm trying to say is that in the classical limit, you can just exponentiate the 2-to-2 process, and then whatever is in front, you can just reinterpret all the small q's as capital Q, so as the classical momentum transfers of the 2-to-2 process. So the final recipe, or the final result, the following. So you can write an effective Eichmann operator that provides you with the Fourier transform of this 2 to n element with n graviton emissions, but increasingly many so, as follows. These, yeah, I'm not sure if I have to rewrite. Maybe more convenient, but e to the 2I delta hat and e to the I real part to delta, in which U is replaced by capital. So this is a very simple recipe, right? This we know from the previous lectures, and this guy, well, it's simply given by the F. Of course, I raised it as usual, but the simple F, so sum over all the particles, in which the momenta are fixed by the Hart process in the way that we just calculated. So there is another subtlety, and then I'm pausing for questions. So here I said that this subtracts the imaginary part. This is, strictly speaking, only true in the case in which we do not consider the I epsilon prescription. So in which we really work with amplitude motivated, let's say, soft factors. What happens when you do include the I epsilon prescription is that there is an extra subtlety here, when you, in particular, when you rewrite this operator by reordering these exponentials. You remember I was saying you have to be careful because the things do not commute. So if you use this I epsilon prescription, what happens is that here you not only subtract the imaginary part, but you also subtract the radiation reaction part. So unfortunately, this is very hard to explain in one blackboard, but hopefully it will be clear the picture I'm trying to give. And radiation reaction, if you include minus I epsilon. And the bottom line is that then this real part of 2 delta actually becomes a real part of 2 delta tilde without radiation reaction. Without 3 PM radiation reaction. Maybe I should use a color for this. I mean, it will not play a big role in today's lecture because, and this is the reason why I'm not showing it in detail, but I just want to give the correct statement. So the bottom line is you can rewrite the soft, you can exponentiate soft emissions and use them to write down an effective Eichmann operator that captures the dynamics of the 2-to-2 process via the Eichmann and the emissions of soft gravitons, which, as you can see, just take the form of a coherent state superposition e to this, the exponential of some creation operator, up to the fact that in the Eichmann you either subtract the imaginary part, if in this guy here you don't include the I epsilon prescription, or here you subtract the imaginary part and the radiation reaction part at 3 PM if you include the I epsilon prescription. Any questions? I realize it's a bit of a sum, but the only way I should be able to present the rest of the material I had in mind. So I think this is the price to pay, nothing else. Okay, now assuming that we are happy with this step, let's use it. So now what we gained compared to the previous lectures is that now we have some information about the radiation entering the final state. Instead of the previous lecture, we were just focusing on the behavior of the dynamics of the massive particles only. So the idea is that we are going to use it in a similar way to the way we use the full S matrix. In a sense, this is just an approximation for the full S matrix in the classical limit, and that only captures the soft emission. So the idea is to again consider, for instance, the stations in the final state of operators, they describing various classical algorithms we were interested in particular, we will focus on the energy momentum and on the angular momentum. And this out state is going to be related to the in state by this. first application we consider is just the waveform. So what is the gravitational field that we essentially put in by including the resummation of these coherent soft graviton emissions? So to do that, we will consider the following operator, just the canonically quantized gravitational field. This A mu more properly should be sum over J polarization F in J mu A dagger J and so on. And for later convenience, let me remind you what is our capital F was. So for the rest of the lecture, I will consider the epsilon prescription. And Fj, remember, small fj was the contraction with epsilon j. Now I will define a small f mu, which is just the PT projection, or if you want, the sum of the polarizations of this epsilon. Okay. So of course, what happens when you insert this operator here inside this sandwich is the usual mechanism. So A pulls down a coefficient of A dagger, and vice versa. So we end up with the following expectation value. So the sign should be right because there is a minus, and A dagger commutator of A is minus the delta function. So now we are left with the task of calculating this Fourier transform, but there is a simplification. So the simplification is that we are not interested in this for generic values of x. So here, in principle, this quantity is formally calculated over all the space-time for x generic, but we want to calculate it far away from the scattering. So remember the picture we had in the last lecture. We assume, we imagine that the scattering happens in some bulk region. So okay, it's actually a scattering, it will be something like this, and we are interested in the radiation that is emitted far away. So we only want to calculate the limit. So what reaches our interferometry experiment is the limit of this quantity for large r at fixed retarded times and angles at theta and phi. So what we want to do is we want to calculate this limit, or more precisely, we want to calculate the limit of a closely related quantity. You remember there was a distinction between this, which is the canonically normalized gravitational field, and the field that actually enters the matrix fluctuation, h mu, which is dimensionless, so it's not canonically normalized, which is root of 32 pi g, the expectation value of this guy. So we want to calculate h geometry. Okay, so was a bit unsure whether to present this in detail, but I think I will try to present it in some detail. There are several ways of performing this test. One way, which is particularly cute, the paper of Cristofori, Gonzo, David Kosover, and Donald O'Connell, is to remember that this can be written as, can be related to the retarded propagator, and then one can use the asymptotics of the retarded propagator. But in a sense, this requires you to know the asymptotic of the retarded propagator. This is very well known, but still. In the spirit of this lecture, I think it would be nice to present it in terms of the method of regions. So let me pretend, let me consider a generic function, say f, has the form of this integral. And we consider the limit as r tends to infinity for u, theta, and pi, or I think we introduce some notation, probably x, a, or well, for u and n mu fixed, right? So again, we are in a situation in which we have an integral. We want to calculate the limit in which one of the parameters entering the integrand is going in some limit. In this case, r goes to infinity. We would like to discuss the evaluation, so we should discuss it using the method of regions. One possibility is to do so. So first we decompose the Cartesian coordinates in terms of these retarded Bondi coordinates. So this is simply t mu times u plus r times n mu, and t is 1, 0, 0, 0, or many zeros if we are in the dimensions, and n mu is our unit vector, like this. And okay, the idea is to introduce a similar decomposition for the integration variables here. K mu, say rho times t mu plus omega times m mu, which should satisfy the same properties. In particular, t squared is our time direction, t dot n is equal to -1, and then squared is equal to 0. So the same condition should be satisfied by m as well. Then, okay, maybe this step I can leave as an exercise. You can show that this can be identically rewritten as f is the integral then the measure on the sphere, let me call it like this. And then there should be this phi of omega m. So instead of phi of k, of course, omega m e to the minus I omega u plus I r omega n dot m. And what happens is that basically one integral is going to vary thanks to the delta function in the measure, of course. If you want more explicitly, this is twice delta of m squared delta of t dot m plus 1 dx. Okay, and now what we are trying to discuss is the limit as r tends to infinity, and you see what can happen is that if as r tends to infinity, this exponent can be very large, so this exponential can lead to very rapid oscillations, which basically kill the integral. This doesn't happen, for instance, when n, say m is equal to n, so in the collinear region, because n dot n is 0 then, let's say plus some correction. I don't know why okay. Then you can use this delta function to show that this n dot n is actually equal to minus z squared over 2. And okay, and then clearly what happens, okay, let me write I r omega n dot n, or minus I over 2 r omega z squared. So you see that the right scaling to consider is that z is small and of order 1 over square root of r. Right? So this is the sense in which we are considering a collinear region. Collinear. And then what we can do in order to calculate the collinear contribution to leading order is just approximate z to 0 everywhere else in the integral. In particular, we can neglect the difference between n and m here, and the rest is more or less the same. So we get f of x collinear contribution is this guy. Then you see here this. You can check by substituting this, that this simply becomes the integral of a d minus 2 dimensional plane orthogonal to well, to t for one and to another direction. Now let you work out the algebra. Okay, this becomes 2 dimensional, and the factor of 2 also goes away. So in practice, we get the d minus 2 dimension integral over z divided by 2 pi d minus 1. Phi, we said we can just approximate omega n, and then the I omega r e to the I omega r minus I omega r z squared divided by 2. And then you see the benefit is that now the integral over z is simply a Gaussian integral, which we can transform. And and of course, we will bring down some factors of pi together with an important factor of 1 over r to d minus 2 over 2. And I now write down precisely. Before moving on, I just wanted to mention that in principle there is another region. Because if we look at this exponent, we can say, okay, but another possibility is to consider omega, that is also small, of order 1 over r. So let me call it, I don't know, regular region. In the sense that it's not collinear. Omega going like 1 over r. And you see by the scaling of this dependence on omega from here, that it will go as 1 over r to the d minus 1 times the possible dependence on omega that this has. So, sorry, omega to the, there is also an omega here. 1 over r to d minus 2, and in particular when this thing behaves like 1 over omega, like in the soft theorem case, it will go like 1 over r to d minus 3, right? Because then we have to also approximate the argument here to be small. So you see, in particular, these are typically associated to the behavior of spherical waves or to radiative solutions, and these instead are associated to static solutions. And in fact, you can check that to leading order, this is independent of u, because you also expand here because omega is small, so there is no dependence on u left. Anyway, let me consider the relevant one. Number case and write down the result. So the result for our metric, now focusing on d equal 4, is that we end up with h mu behaving as R goes to infinity for fixed u and n. You get factor of 4 g over kappa r. And then, in principle, as an intermediate step, you will get an integral from 0 to infinity d omega over 2 pi, well, I pi actually, because there is also an I that comes down from this Gaussian integral in d equal 4 f and then the complex conjugate, which has a minus because of this I, an integral from 0 to infinity. Well, sometimes I'm using two different fonts for the small f's, but I hope they are readable. Star. Okay. Now we can use the property that this f satisfies, and you can check explicitly from its expression. Not to get confused, we can think of using physical polarization that are real, but there is no need to actually. Here, remember, there is an overall projector which doesn't care about the star. So the property is the fact that f star of omega is minus omega. And then you can see that these two integrals recombine, right? Because if you change omega to minus omega here, the measure doesn't change. This you get an extra factor of an extra minus sign from the explicit omega. Of course, you have to flip the integration end, and this, thanks to this property, becomes on f of omega. So what I'm trying to say is that this is just a single integral from minus infinity to plus infinity. Okay. Very good. So the last thing that we want to do is to plug in the explicit expression and evaluate. By the way, one thing that I did at some point and nobody complained is the fact that you remember there was a cutoff on the frequency at some point. So in principle, the integral should extend from minus omega star to plus omega star. What we are doing here when extending it to minus infinity and plus infinity is that realizing that it's only valid for large u, right? Because small omegas or omegas restricted between some cutoffs minus omega star and omega star actually means large u. So let me redraw the drawing here. Suppose we are at 3 plus and our experiment is here. We are just, there will be some values of u for which we don't get a reliable prediction, but we get a good prediction for omega that tends, for u that tends to plus infinity or u that tends to minus infinity. Okay. So the last step, plug in the expression for this step and use the identity. So you remember this goes like basically 1 over omega, but you have to be careful about the sign that we were discussing a minute ago, right? It could be plus 1 over omega plus I epsilon or 1 over omega minus I epsilon, depending on whether this is incoming or outgoing. So more precisely, the combination that you end up with is this one, 3I pi, 1 divided by minus a sign that I'm calling eta A, and it's positive for the outgoing state and minus for the incoming state, times e to the I omega eta A u. Sorry, to the minus I omega u. Then what you can do is you can change again variable. So for instance, I'm changing omega to go to minus eta A omega. We get I omega eta A u. And this we recognize as an integral representation of the theta function, right? Because when this combination is positive, we can close in the upper half plane, and this fits the pole that is in the positive, well, in the upper half plane, along the positive imaginary axis, and this simply gives the theta function of, while in the other case we can close in the lower half plane, that there is no pole there. This gives a theta of theta AU of any sign. And finally, plugging back here, we end up with our expression for the waveform in the large time approximation, which is dual to the low frequency approximation, of course. So that's infinity gm over r g, sorry, 4g over r. Then this is projector. Then the sum PA mu, oh sorry, PA rho is sigma divided by, well, minus eta n PA dot n, because I had to multiply and by minus eta squared in order to bring it up, times the famous theta function. Okay, now we are in a position to make some comment, finally. So what this formula is saying, you remember that this is only reliable for large u, large actually absolute values of u, right? So what it's telling you is that for large negative u, and this guy is negative, the waveform simply asymptotes to the value of this combination where the sum is restricted to the incoming state, and for large negative u, it gives instead the same expression but with the sum restricted to the outgoing state. So this is your waveform or some polarization of your waveform. As a function of retarded time, the calculation we did does not predict its values for generic u, say u of comparable order to the impact parameter, just to have an order of magnitude in mind. And instead it tells you what happens, that for large negative u is just given by this expression with sum over the in, let me call it like this. Then there is something happening, and at the very end it will go, going to be like sum of the out. Okay. And this is, well, more precisely, the difference between the two values in the far future and in the far past is the so-called memory effect. So the fact that the memory, the fact that the waveform in general not tend to zero in the past, its actual value can change precisely even thanks to these contributions coming from soft gravitons. Note that in particular in our in our discussion today, we had in mind the effect of these in and out states being the massive particles, so 1, 2, 3, 4. However, the formula is more general and is also valid when there is an n particle process. So this sum over A in could be any number of initial and also final states in the out case. And moreover, just like the Weinberg theorem, it's also valid even in the case in which some of these particles are gravitons. So in particular, there can be some contributions to this sigma out that come from the emissions of soft gravitons from hard gravitons. In the case, and this is the case of the so-called nonlinear memory effect, which in fact we will briefly discuss later today. So maybe let me conclude this first half of the lecture by mentioning the connection with the super translations. So you remember last time we concluded by sketching this derivation of the photosymptotic symmetry of symptotically flat spacetimes, and in particular, you remember there was a set of angle-dependent transformations which reduce to ordinary translations with for some choices of this parameter p. So in particular, when t is 1, or sin theta cos phi, and theta sin phi, or cos theta, but more generally, they parameterize some angle-dependent translations which are known under the name of super translations, and they transform. So the metric, this h mu, when you project it on the two vectors orthogonal to the tangential to the sphere, so a mu and a mu. And you can also take the traceless projection because actually you know that this guy is traceless in the on-shell description. So this is what people call CAB times R, I think, in the convention we had last time. And the transformation of this CAB under a translation, super translation, is given by this expression, T u CAB minus Laplace in the sphere, where all these derivatives and the Laplacian are defined intrinsically on the sphere, so they are covariant derivatives on the sphere. And you notice that this is indeed traceless, as I was mentioning. So the connection between that expression and superposition is the fact that each of those terms can be actually written as in this form. In particular, you see we are calculating focusing in particular on this structure here, P divided by P dot say n tt projection. And so before doing that exercise, let me stress the difference between two key properties. One is the memory. So the memory is really sigma out minus sigma in. And the other is the static field, which obtains by taking P3 and P4 and approximating them to minus P1 minus P4. So just neglecting the deflection. So in that case, the field you see becomes really independent of T, and is given by well, just sum over in PA PH.
Sorry, what do you call sigma out?
Yeah, just the
overall
combination. It's just a bit schematic instead of just rewriting everything. Just that expression with A restricted to out or with A restricted to in. Yeah.
And no pi mu rho. The tensor.
Yeah. Also pi. Sorry, sometimes I'm omitting it, but of course it's always there. Let me write it like this. Thanks. So the difference is that, as we will show in a second, this thing can be, in principle, always super translated away, in the sense that I will write down in a second that T, such that if you perform a super translation, this behavior of this component of the field, which is the static piece, so the one in which you neglect deflection, is 0. In particular, the value at minus infinity, you see just the sum over the in, can be set to 0 if you want by performing a super translation. Instead, what you cannot change is the memory, because in particular, this combination is independent of time. So you could take the difference between the thing that you added or subtracted at future infinity and the one at minus infinity. You will just it will just be invariant, right? So this is invariant under super translation. and instead this can be set to 0. So let me write down the magic function that does the job. Okay. So the statement is that if you perform a super translation with this t, you will kill the static piece. So to show that, the proof is actually very simple, but it relies on an identity. So let me start by trying to calculate this square bracket. So let me start by calculating dB t, and just focus on one of the two terms, of course. So let me go to G. Then the first, what is happening? So there will be a PA dot n, which just gives dB PA, sorry, dB n dot PA, and the log. And then the log is, of course, the derivative of the log is one with its argument, the m doesn't matter. So this just cancel, and then you use again v dot b. And then when you calculate the second derivative, you just get g dB PA and PA with b and dot PA divided by PA dot n. And then we get things that are proportional to dA dB n, right? Was there a bracket? Yes. So now the issue you see is that I will need to substitute it in here and subtract its trace. This is nothing but the trace of this first object, right? And there is a useful identity, namely the fact that this dA dB n hat is minus the metric times n hat. This you can actually show by embedding the sphere in Cartesian space. It's a nice exercise in, let's say, Riemannian geometry. And of course, the derivative of the time component is 0, so you don't even write it. So what happens is that when you plug this here and use this identity, all the pure trace pieces just go away, right? So what I can do is I can rewrite this as the delta t CAB equals to the TT projection, the traceless projection PA divided by PA. And this is, well, this is precisely the TT projection of by the way, this dA and dAB are the vectors on the sphere. So this is really the TT projection. This you can really rewrite as the TT projection. Or if you prefer, you can contract that thing with dA mu, dA nu, and then you will find exactly this combination. So you see, what we showed is actually a bit more powerful than what I said. What we showed is that even playing around for independent A indices, we can just super translate as will any term in this combination. We could set to 0 the component of particle 1, but not the one of particle 2, just the one of particle 2, or both. So it just tells you that the key point is that this contribution does not depend on time. So the static value of the field is really super translation dependent. Instead, the memory is invariant because it would add and subtract the same to this and to this bit. The last comment, which is somehow one of the reasons why people are excited about the connections between soft theorems, memories, and these super translations or asymptotic symmetries, is the fact that the memory itself, you can interpret it as the action of a super, as the difference between two configurations that differ by a super translation, right? In the sense that also S out, you can rewrite it as S in plus a super translation. So this is why people think that in some sense, these super translations have a physical manifestation in the memory effect that could be measured by experiments.
Yes. When you talk about the super transitions, are you also including L equals 0 and 1 moles? Or
That's a good question.
because
I think here they are projected out by this TT projector.
contains also L equals 0 and
Yeah, but they are, of course, here they are. So just for the rest of the audience, people is wondering about these objects, what they do. So what happens when you plug them here is that these are killed by these operators, right? So these, in fact, these are precisely zero modes of this operator, and I think this, yeah, the analogous statement is true on the other side, right? If you try to write down something,
yes,
it are just killed by this pi mu rho sigma. So yeah, in a sense, the TT waveform is not sensitive to them.
yeah.
What is sensitive to them would be the value of the field without the TT projector, which is actually a subtlety that I wanted to mention later in the calculation of the angular momentum, because as you know very well, it's important. Yeah. So in a sense, here we are just discussing the TT projection of the waveform and not also the Coulombic field that involves longitudinal components. Yeah. By the way, this the failure of this F mu to satisfy the word identity, you remember earlier, it was proportional precisely to the sum of PA nu times a factor with A in the in. And this, in a sense, is really the Coulombic charge of the problem, right? Because it's the total form momentum of the initial state. But and a similar statement would be true for the photon theorem. So we will find would be the sum of the charges, the Coulombic charges of the initial state. So in a sense, really including this Coulombic field is tantamount to keeping these longitudinal components in the F mu and not projecting them away. This will play a role later on in the angular momentum. So I think it's a good time to take a short break.
Okay.
Continue. Today, the second part is going to be basically continuing the idea we developed in the first part. Is that we are going to use this soft operator, but insert now different operators in the sandwich. So if you want, the iconal operator is going to still describe the same final state as before, but now we are going to insert different O's in the sandwich, out, out. And we will start with the energy momentum. Soft energy spectrum we will calculate. So we insert the energy momentum operator, which we can write in any gauge we want. Say, for instance, in the London gauge. Let me make this P alpha. This is D mu rho sigma integral K alpha D mu sigma, and this could be, for instance. But this could be equivalently written as sum over the physical polarization. This is just for simplicity. So this D is just a combination of half eta mu rho, eta mu sigma, eta mu sigma, eta mu rho minus eta mu. Okay, so by now you know the drill. We insert this in the cycle operator, which is an exponential with f and f star multiplying in a and a dagger. A dagger will pull down the coefficient of a will pull down the coefficient of a dagger, and everything boils down to the following. Integral. There is a cutoff in the frequency that comes from the fact that we only inserted gravitons up to some soft frequency cutoff here. So let me write it as a star. A alpha f mu f rho sigma, or f mu, because remember these involve the TT projection, so most of this structure doesn't actually matter. And then here, what we can do is use the word identity, because you remember the key point is to check whether or not the f mu appears with enough powers of k or of omega, and here you can check that this is indeed the case by writing down the measure explicitly. So now we use k mu f mu equal to 0. This is correct here. And then we can rewrite the contraction, which would involve the sum of physical polarization, as the contraction with the usual the Donder gauge structure. So F mu, eta mu rho, eta mu sigma, minus 1 over d minus 2, eta mu, eta rho sigma, F star. Here actually the star doesn't matter precisely because the epsilon prescription doesn't matter. So this is the object. And now, actually, the only part of the result we are reliably calculating is the contribution coming from soft gravitons, so up to some cutoff omega star. So the most sensible thing to do is to consider so pictorially what we are doing is that there would be a whole spectrum, the dp in the omega, or focusing on the time component, the energy, there will be a whole d in the omega as a function of omega, but we are only calculating reliably the contribution up to some omega star. So let's take the derivative with respect to omega star and evaluate directly the omega in the zero frequency limit. It's just, well, the derivative of this thing with respect to omega star. So let me not dwell too much on the details. You have to, so what happens is that the derivative with respect to omega star effectively removes the integral over the frequency, right? So you end up with an integral over the angles, or more formally, if you want, you can write it as omega star delta function of omega star minus k0 times f star f. Here you remember, when I'm not writing anything, I mean contraction with the structure. Yeah. And the integral to evaluate eventually is exactly the same that we already discussed in the second lecture when dealing with the imaginary part of delta 2. So let's write it down. We have an 8πg that comes from the kappa squared that these two factors bring. Then you have two sums over A and B, again coming from either of this factor, and then you have the contraction of PA nu, and PB rho, PB sigma with this structure, which that just brings sigma AB squared minus 1 over D minus 2 times masses times these signs that we have to be careful about, and sorry, times the mass is squared, of course, and then this integral here. And then each, of course, brings a factor of PA dot K, PP dot. Okay. So now this integral is the remaining integral of the angles is the one that we already mentioned a couple of lectures ago. So here you end up in an integral over the angles. Arc cosh. And let me remind you that these sigma AB are just an invariant built from the momenta. So one way to evaluate this, as I mentioned, is to go to a rest frame, but this may not satisfy everybody because you have to know that this is Lorentz invariant beforehand, which it is, but it's not obvious beforehand. So maybe another way, if you want bonus point to evaluate this, is to relate it. You can also do it on Mathematica, if nothing, just observation, you can relate it to the imaginary part of a loop integral, which you can then evaluate with the Feynman or finger parameter. and then you can check explicitly the dependence on this reference vector k, which is a time-like vector, actually drops out. So yeah, just an aside. So in the end, you can evaluate the integral explicitly and get a prediction for this zero frequency limit. You can write down that commented. So this is the zero frequency limit of the emission spectrum, and it's V over pi. Let me say equal for today. Eta A, eta B, arc cosh. Yeah. So, a few comments. The first one is that you remember we only used in this writing the approximation coming from the soft limit, but we didn't assume anywhere that P3, P4 be related to P1 and P2 by small deflection, right? So in particular, in this expression, when you interpret it, applying it to a 2-to-2 case, so when A and B take values 1, 2, 3, 4, Q can also be a big deflection. Can also be a process where two things are interacting strongly and then deflecting in a non-trivial way. The only price to pay is that this is only valid for the contribution to the emitted energy that come from very soft gravity. The second comment is that although in order to discuss the step coming from the the Fourier transform of the momentum space exponentiation, I use the Eichner exponentiation, which we only discussed for 2-to-2 processes in detail. This formula is actually, this is actually more general and also valid for n particle processes. In fact, another way of deriving it is from the soft theorem involving that is valid for the waveform itself, just classically, without ever talking about these amplitudes. And that has been shown in particular in papers of Sen and collaborators to be true for generic number of particles. So this you can apply to rather general situation. Moreover, it does not depend even on the details of what these particles are. They could have different spins or different, say, properties, tidal excitations, for instance, and the formula, as you can see, is universal in the sense that it only depends on the momenta and in the initial and the final.
Sorry, it was sigma square AB minus 1 over D minus 2.
Yeah, I'm seeing D equal 4 now. Yeah.
Okay.
Otherwise, this integral is a bit trickier, but
okay.
And also the behavior in the frequency should be rediscussed. Yes, this is valid in D equal 4. So one thing that we can learn from this is to learn what happens to our beloved PM expansion. So you remember a couple of lectures ago we discussed, we briefly hinted at the fact that if we first take the PM expansion of this expression for now for the 2-to-2 process, if we first take the PM expansion, so the expansion for small q restricted to leading order, this you can check that this gives a contribution that goes like q squared. This is actually analytic in q. So g times q squared starts at order g cubed. And we had a small puzzle because it seemed that this g cube contribution at high energy becomes very large. So the right thing to do is to discuss both limits in order to understand what happens. So the first, option 1, the small q, and then the expression is the following. G over pi c squared 1 pm, and then there is a function calligraphic I sigma. Let me rewrite it just for completeness. We already saw it a couple of lectures ago, I think. plus 2 sigma. 2 sigma squared minus 3 sigma squared minus 1 to 300 half cos of sigma, where sigma is the sigma 1, 2, right? Now the puzzle with this result, so then it would be higher order correction, in say order G4, etc. The puzzle with this expression is the fact that this calligraphic I sigma involves this arc cos, and for very large sigma leads to a behavior like this. If you divide by the total energy, which will be the square root of the S Mandelstam invariant, and then you estimate that this bin is of order 1 over b. So soft frequency means wavelength larger than the impact parameter. Then you can estimate the total energy that is lost just by this strip that I drew over there in the zero frequency limit, so in the soft limit. And then you end up with an estimate for this thing in the limit as sigma goes to infinity that behaves like theta 1 pm cube, times some factor, which is not really important, times the logarithm of sigma. So this is not very good because it means that the fraction of the initial energy that you lost can be arbitrarily large, right? This is small and fixed in the energy limit, but this can be arbitrarily large. So this doesn't make any sense. Now we are in a position to solve this puzzle because we have an expression that does not rely on the small q approximation. So the right thing to do is to first take the limit for high energies and then take the small deflection limit. So option 2 at this point. So you first take the relativistic limit. And then you end up with this. So this would be the limit in which the energies of the cutting particles, so say E and P, are very large compared to the masses. And then you end up with this, or P over pi S log S would be E squared, they are exactly the same. S log of S divided by S minus squared plus Q squared log of S minus Q squared divided by Q squared. So this expression follows from the ultra-relativistic limit of this expression for the 2-to-2 case. And then only later consider the small deflection limit, which means you remember, is equal to 4 q squared is 4p squared sine of theta squared over 2, and then you consider theta small. Then you get gs theta squared divided by pi 1 plus log of 4 divided by theta squared. So basically, you see there is still, the contribution is still order g cube overall, let's say. Theta to a leading order is ge over b, so g times g squared g cube. But then there is a logarithmic dependence that is not on the velocity or on the Lorentz factor, but rather it's a logarithmic dependence on the angle, so on the coupling, which means that what we are calculating is non-analytic in the coupling. And this, in a sense, explains in hindsight why our PM approximation was breaking down. In fact, by looking at what appears at the functions that appear in the original expression, you will see, if you write them down explicitly, that one of them can be written down as arc of sigma plus q squared divided by 2, one of the masses squared, will be 1 or m2, and then similar, 1 of course, there will be sigma divided by sigma squared minus 1 when A and B are equal to 1 and 2. Then there are other combinations, in particular the combination coming from 1 and 4 is this kind of structure. Sorry, 2 squared. And the key point is that this function, so the function arc portion of x divided by square root of x squared minus 1 is actually analytic for x bigger than minus 1. So it develops a branch cut when this argument is equal to minus 1. Of course, it's an unphysical region, but analytic complex analysis doesn't care. So there is a branch cut. So the series, the power series expansion of this stops converging when q is of in absolute value. So the square is equal to minus 4m squared. So in particular, the branch point. And therefore, it is already tells you that the PM series, which is an expansion for small q, will stop converging roughly when q is of the order of the mass, or if you plug in this expression when theta is of order of 1 over, sorry, when sigma is of order 1 over theta squared. So let me say that the PM expansion is limited to sigmas that are smaller or equal than 1 over theta squared. So this is the sense in which we say that PM expansion means going to generic velocities. Velocities can be large in the sense that sigma can be large because theta is small in the PM expansion, right? It's of order, say, 1/10, for instance. But then there is a bound in the validity of the expansion. Question? Okay, then let's move to the last topic of today, the angular momentum. So to do that, again, we will apply the same logic, but now we will see that there are more subtleties, of course. So the logic is that we are going to insert our favorite operator. Now, instead of being the energy momentum operator, it's going to be the angular momentum one. So we are going to insert just the canonical angular momentum that you can derive from the Euler theorem. And again, I'm writing it down in the Donder gauge in particular. Okay. So everything works as expected, although there are some derivatives which might scare you. Each of these guys pulls down its companion from the exponent in the expectation value, and then we end up with this that I'm going to call TT for a reason that is going to be apparent in a second. And the reason is that when these guys pull down what is in the exponent of the Eikonov operator, they pull down the TT projection of the F minus I 1/2 F star mu K alpha d K beta F mu plus, sorry, minus F, no, plus was correct, twice F mu alpha F beta mu. Should be round. And F, let me, was the TT projection of capital F. Okay. And I think there should be the double arrow. The double arrow for me means including the 1/2 F double arrow G means 1/2 F dg minus GDF. Okay, double check. Okay, now looks good. So now the issue, you remember, is the following. In the previous calculation for the energy momentum, at this stage we wanted to rewrite F as the TT projector of capital F, and then get rid of this TT projector in favor of our beloved eta, mu, eta, rho, sigma, blah blah blah, using the word identity. So using the fact that K mu F mu is 0. However, what you can see from here is that there is no extra power of K mu in this calculation. We have one less power of K mu in front, so of omega. So in this case, the fact that F mu does not satisfy identically the word identity is actually important. So we have to discuss this. However, what you can show, no matter, so for the moment, let me write JTT equals J alpha B plus terms involving N dot F, let's say. We call it F. And we will discuss them later on. Okay, hoping that we have time. So for the moment today, let me focus on the contribution that comes by pretending that N F is 0, but we will come back to those guys. Okay, so then the expression is what you imagine. It's the integral over K. And then I'm not writing the indices, so I mean that they are contracted with our beloved London structure. K alpha Vf K beta plus twice capital F star mu alpha beta mu. And let me calculate this to begin with. So of course the benefit from a calculation point of view of this expression without the TT is that it does not involve the reference vector that appears in the TT projector, and the manifest Lorentz invariant does not depend on the fact that you perform the TT projection in some frame compared to another, and it's easier to calculate. In fact, you can reduce it to integrals of the following form. So here is the step I was mentioning earlier on. You remember there was some issue about this I epsilon prescription and the factor of 1/2. So here we can just use the expression for F without sending I epsilon to 0. Just keep it as a small parameter. And then you can reorganize this expression in terms of one type of integral, which is the following. And then we can work in equal form. Sine, so we have K0 sine delta K mu theta function of omega star minus the absolute value of K0 divided by in this way. So you can write J alpha beta equals. So you have to play a bit around with the sums that appear in this F and F star in order to massage the expression in this way. So there is I alpha squared divided by 2 sum over n m sigma n squared minus 1/2 that comes just from the contraction in this term, n squared this integral K alpha P n beta minus I alpha squared sum Pn dot Pm. There is a simple contraction in the term that comes from this distribution here, Pn alpha Pm beta. Pm dot, where K now is this integral. Okay, I just wanted to write some intermediate steps in case someone wants to reproduce the calculation. So the idea is that you can rearrange the sum here in order to rewrite it in this way in terms of this integral, which as you can see involves a sum over positive and negative frequencies now, with a different sign prescription that comes from the theta functions in the original phase space measure. So that's why there is this absolute value here. And now the benefit of this is that you can actually perform the integrals very similarly to what we already did in the previous example. So this integration actually factorizes into an angular integral and an integral over the frequency. The angular integral is exactly the same. Sorry, this should be squared. Sorry about that. So you can do the Passarino-Veltman and the composition with this K mu as usual, but the scalar integral is exactly the same. The new ones, the ones with respect to the frequencies, now are integrals with respect to positive and negative frequencies that are cut off by this omega star. So in particular, we end up, for instance, with something of this type. And in order to make apparent that I'm not sending I epsilon to 0, let me give it a name. I don't know. Small lambda, for instance. Here, minus. So what you can do, you can just evaluate this. This is an elementary integral you can do by partial fractions, and then send lambda to 0 at the end. And then you can find minus I pi eta n divided by eta n. You remember this is plus if the state is outgoing, minus if the state is ingoing. This is a compact way of writing them. And then there is a similar companion integral where you get the square of one of the two. So that's substituting this into the expression here, you find the following result. I try to put this piece of the blackboard maybe. So this J alpha beta, or the thing we got from this soft operator or soft plus static operator is sorry about that, G over 2 sum over alpha and beta. There is some function, we can call it C. And the function is the following. Sorry, it's a bit long, but after I will comment. Very good. So you see, the issue here is that in this step, the dependence on the frequency cutoff has dropped. So what we can deduce is that now we have obtained a result that in principle we would have guessed would depend on the cutoff up to which we integrate in this original integral, right? There is omega star. But now we can simply send it to 0 because the answer doesn't depend on that, which means that the result only depends on the 0 frequency limit of the integral. So it has localized, if you want. And this actually matches what you would get from this 1/2 theta function, the delta function approximation trick that we used at the beginning. So this has the right factors of 2 using this integral as I wrote it here. And okay, the second comment is that, as usual, this is a contribution that depends in a very simple way on the external state, no dependence on spin, tidal deformation, etc. Just depends on the momentum. It is also valid for n-body processes, just because the stop theorem doesn't rely on the fact that we restrict it to the 2-2 case. And okay, then there is another comment I want to make about the nonlinear memory contribution, but let me postpone it to a second. Two points. The first is that a similar issue appears if we want to discuss the high energy limit. So you remember we have these two limits. So one in the PM limit in the so small q approximation, you can rewrite this as j minus g. So if you expand this for small q, there's a nice simple expression. So why not write it? P1 minus P2. This is for the 2 to 2k. Q alpha Q beta calligraphic I, the same function as before. So in principle, this quantity is as ill-behaved as the previous one for large sigma. And but in order to discuss, before discussing the other regime, so option 2, take first the high energy limit and then take the small deflection limit, let me come back to the subtlety I mentioned here, and then for the moment I neglected. What happens to those terms? So let me maybe write down a box here about these R terms. Let me call them. Or if you want, TT versus non-TT. So what you can show is that if you define the TT projection in the center of mass frame, these extra terms do not contribute to the angular momentum proper, so the spatial component ij. So apologies, in my notes and also in the literature, usually we use this calligraphic J instead of J. I don't know why. At some point I start using ordinary J. That they are the same. Maybe let me keep calling J. So JTT is actually equal to J. This is some magic that you can derive by painstakingly deriving this in general, keeping this R. It's a bit ugly. It's not just a simple expression. It has many more terms that I'm not bothering to write down on the blackboard for today. And then you can just plug in the value for this R that depends not only now on this longitudinal component, right? So sum over the initial state, but also on the time delta of omega, but also on the form of the TT projection, which you define in the standard way in the center of mass frame. The benefit, the reason, I mean, the intuitive reason why this simplification occurs is that in the center of mass frame, by definition of center of mass frame, this is the total energy of the system in the time component and 0 in the spatial component, right? Because when the center of mass frame is defined by the fact that the initial center of mass momentum, spatial momentum is 0. And this is somehow makes it more reasonable, I hope, that they don't contribute to the spatial component. Instead, they do contribute to the mixed 0i component. So I0 T is not equal to I0 not T. And let me write down for you the expression. And I think I want to do it over there. So you can have a look at an appendix of our work with Rodolfo last year if you want to know more. But the bottom line is that JTT in the center, always in the center of mass frame. So with the TT projection defined in the center of mass frame, this is equal to our prime downstairs, J alpha beta without TT, plus a contribution C or sigma A sum over the incoming state P B alpha C A B. Yes. Where C is the exact same function I write in here, but then it's evaluated at sigma A, which are defined in the center of mass frame as the energy of the particle in the center of mass frame divided by the mass of the particle. Or if you want more covariantly, as PA, P1 plus P2 dot PA divided by PMA with an appropriate sign. Okay, and you see that just by sanity check, if we go to the ij components here, you get a sum over b of the spatial components of pb in the in state, which is 0. So this drops and you get back the statement over there. Otherwise, you have a correction. So the one nice feature of this, so it's a bit less nice in the sense that it's defined with respect to a specific center of specific frame, although it's very naturally intrinsically defined for a 2-to-2 process. A nice feature that it has is that it has a nice high energy limit. So in the UR limit, you get this simple expression, JTT alpha beta, so similar to the one that we had for the spectrum. It's just the log of S divided by Q squared minus 1, P1 minus P2. And you can check again that in the if you were to take the high energy limit of this, it would be ill-defined. Sorry, of this would be ill-defined, but only for this I0 component. So not for the usual energy momentum. Of course, it doesn't matter. For the usual angular momentum in the center of mass frame, it doesn't matter. And there was an additional remark I had in mind. Yes, the meaning of as you know, these things appear in a tensor because they are related by Lorentz invariance. The meaning associated to the spatial component is the invariance of the system under spatial rotations, and the others are associated instead to the invariance under boost. So in a sense, they are the boost charge instead of the rotation charge. And if you want, whereas the angular momentum, we are all familiar with it, it's just a conservation of, say, the fact that P times B is the initial angular momentum, and then the total must be conserved. These are instead associated to the position of the center of mass frame, of the center of mass, really the physical center of mass of the system, at some fiducial time, which for an isolated system doesn't change, and instead here, if there is radiation, or in particular in this case, an interaction with a static field, it changes. Questions about this point? Okay. Another thing is that instead, if you were to define the T projection in a different frame, this formula changes. And in the appendix of the paper, we have also a formula for the IJ components in particular. They are not, so those depend, unless you define the T projection in the center of mass frame, the distinction between the two terms also survives for the IJ components. So in particular for the rest frame, for instance, they are different, they give different results. The last point I wanted to make about again about the regime of validity of these formulas in a sense. So we said, for instance, expressions of this kind and the similar one we had for the energy momentum, for the energy spectrum, are valid for generic number of particles. Actually, could be mass 1, mass 2, mass 3, mass 4, and mass 5 in case they split and produce something else. Or it's more relevant for 2-to-2 gravitational scattering. They're also valid to calculate the contributions due to the emitted gravitons, because after all, originally it was also in the spirit of the Weinberg theorem, you can just think of the gravitational scattering, the realistic one, as a particle 1, particle 2 in the initial state, particle 3, particle 4 in the final state, and a bunch of gravitons. Okay, you can just apply this formula. However, you have to be a bit careful, so let me discuss this point. So this would be the contribution due to the nonlinear method. So the key observation is that even the original expression for F, right? We wrote it as a sum over all the particles minus I epsilon. Let me neglect the I epsilon notation for a second. Then what we want to do, actually, in order to have formulas that we can manipulate more simply, is to restrict the sum over the particle, I mean, say AM, the massive particle. This would be really 1, 2, 3 now, before, plus an integral over the phase space distribution of emitted gravitons, let me call it rho k, of the same exact function applied to gravity. And now I have to decide about the notation. Okay, k prime dot k. This is a function of k. Okay. So this is really the nonlinear memory contribution. Now the issue is, how do you compute this distribution of emitted gravitons? Well, in a sense, this is you can use either KMOC or the Iconad to deduce that. It would be the number of emitted gravitons per unit phase space volume, right? So instead of inserting, say, the energy momentum, we should insert the number operator, and this just brings down the waveform square. This we will see more clearly in the next lecture. But to leading order, you can just think of applying KMOC to the operator a dagger A without any K, and this will pull down, I mean, this generates a graviton in the final state, this generates a graviton in the initial state, and this is simply the 5-point amplitude squared, which to leading order is just the waveform square. So this is particular, we can, to leading order in G, we can approximate this with the 5-point amplitude at 3 level, and then we will have a leading correction given by the next leading order waveform. Okay, so now the idea is to apply this operation to all the sums that you see in the blackboard that you have in your notes, and see what happens in order to get the contribution from nonlinear memory. That is, in a sense, is already in the formula. Maybe let me do it. Well, let me do it first for the angular momentum, since I have it on the blackboard. The idea is that we have to substitute either of these sums. So of course there is a contribution in which A and B are both restricted to the massive object, and this is what we already discussed in a sense, right? We had already had in mind the massive object earlier on. Now there will be a contribution in which A is massive and B is the graviton integral, or vice versa, so there will be actually a factor of 2. And then there will be a contribution in which both are integrals over the frequency, over the phase space of leading gravitons. Now, however, this leading order is over the G cube, right? So I will evaluate this only perturbatively, and the leading contribution, of course, is the mixed term in which you get a sum and an integral. Very good. So the idea is to assign this B to be particle number 5, let's say, which is the graviton over which we are integrating, which is massless. Now the issue is that sigma tends to infinity for when one of the two particles become massless, right? Because you can write sigma as signs, and then PA dot PB divided by A and B, right? Let me call this zeta, or zeta divided by MA and B. So, okay, for some factors, it's really harmless. So, for instance, this term simply tends to 1. This term simply tends, factor this simply tends to 1. And also these simply cancel out, right? Sigma divided square root of sigma squared. So the only issue is to discuss what happens to this arc cosh. Let me see if I... is the log of and perhaps it's better to write as 1/2 the log of sigma AB squared plus divided with sigma, sorry, not squared. Okay, and then we can use zeta, which is a better value for this problem because it's constant. So zeta AB plus the root of zeta AB minus MA and B divided by, here it's unreadable. Let me write it in another option. I'm doing this in detail just because I want to illustrate this point minus MA MB divided by Z. Yeah, reasonably readable. So now you see what happens when you send say MB to 0 is that in the numerator you just simply get a factor of 2Z, and in the denominator you get 0, or in other words you have to expand, right? You will get 0 plus something that is suppressed by the mass squared and factor of Z, I think. So basically what happens is that you get a number which doesn't really matter times Z squared divided by 4 squared. And make all these factors and bring out a factor of 1 or 2. So this tends to logarithm of Z divided by MA and B, which is a logarithmic or a collinear singularity, right? The fact that these things tend to 0 when one of the objects is massless. Now, the useful feature is that these singular collinear contributions always go to 0, thanks to the fact that gravity has no collinear singularity. And one way to see this is to substitute them explicitly either in that expression or in the one for the zero frequency limit. Maybe in view of time, let me not do it directly. Let me give the result. Perhaps I can erase over there. So for the angular momentum, I'm oscillating a bit because, of course, the case of the zero frequency limit is simpler. Let me write the zero frequency limit. So if you go back to the expression that you have in your notes and substitute this operation, you get the contribution due to nonlinear memory, the leading one, is simply given by minus 4Z over pi. And then let me call lambda the scale that appears inside here. It doesn't really matter, right? It's the mass or 4 times the mass is just a scale that should go away, right? There is a sum here, it's over all the states of the massive state. Maybe I should call it AM, be consistent. Lambda. Okay. So you see here appears the arbitrary scale or the singularity, the collinear singularity. However, you see that the coefficient, if you separate the log of something plus the log of lambda or minus the log of lambda will multiply the sum over all the massive states P8 dot K, but the sum over all the massive states must give the frequency of the graviton, right? Or if you prefer, actually in this case we give the graviton, the emitted energy via gravitons, which has 3 more powers of G, because leading order it's like rho K, right? And therefore it starts at the same order as the terms that we neglected when we said that we were neglecting the square of A. What is it? At some point we said there will be 3 terms, one in which both are integrals, and this is of the same order as those terms that we neglected, so it doesn't matter. Will be taken care of when someone will take care of the higher order calculation. This, let me write it down. Log lambda, I guess, minus p rad dot k, which is suppressed by an order GQ. So this doesn't matter for the leading contribution in particular. And in fact, the leading order contribution, you can just write down these 4 terms explicitly and expand for small g, and then the leading contribution is simply given by so what happens is that you can Taylor expand basically, right? Because you have P4 equal to Q minus P1, etc., and Q is small, so you get something proportional to Q. you get q dot k log of say p1 dot k divided by n1 and p2 dot k plus, in principle, so let me do the power counting once again because it can be a bit confused. G, one power of G from here, one other power from G from here, and then here in principle there are three powers of G, right? Because this is the spectral initial rate, which is proportional to the 5-point amplitude square, so GQ. So this is order G to the 5 and in principle G to the 6 for reference. So very high PM in a sense, although this is all trivial math. And the key point here is that particularly is a property that we will discuss more in detail next week, but here to leading order, I'm approximating, as I said, this with A0 tilde OK squared, the 5-point amplitude squared. But the 5-point amplitude in momentum space is real. So it means that the star corresponds to sending B to minus B, simply because the Fourier transform is e to the I B dot Q something, right? So if this something is real, I say something trivial here, just we are all very tired. So the star of this is equivalent to sending B to minus B. I think we all agree. So it means that this combination is even if B is sent to minus B. So in particular, if we send B dot Q, sorry, B dot K to minus B dot K. However, for this integral here, B dot K going to minus B dot K is simply a change of variable. It would be like Kx. Suppose we align B in the x direction, it would be Kx that goes to minus Kx. So this combination is odd because Q is along B. This combination is even. And this combination doesn't depend on K dot B, right? It only depends on K dot 1, K dot 2, which are the longitudinal directions. So we conclude that this odd quantity is odd in Kx going to minus Kx. So this is actually 0. So it means that the first order, we have to worry about the contribution to nonlinear contribution due to nonlinear memory to the zero frequency limit of the spectrum is actually G to the 6, not G to the 5, although power counting would suggest a bit G to the 5.
So it's not the one coming from the mixed term.
It's still coming from the mixed term, but it comes when you insert the one loop waveform. Yeah, the next reading. And the same identical mechanism works for the angular momentum. Let me not bore you with this since it's very late. You can write down this mixed term that comes from the sum of the two. The difference, the only non-trivial difference, is that now the collinear singularity would survive if you were to use this expression, and instead goes away if you use the TT expression. However, it only matters for the zero I component, so for the mass dipole loss, but not for the change of angular momentum. This does not depend on this lambda in either case. And there, the bottom line is that maybe we can do the power counting there. There will be a G, then will be this GQ coming from the measure, right? This rho, and then naively we will say that this matters. This effect matters for the angular momentum loss at order G to the 4, but instead the same parity argument of the integrand applies and allows you to show that this. So in other words, I'm trying to say J alpha beta due to zero frequency mode. Zero frequency. Due to nonlinear memory, this cross term is actually of order G to the 5. Okay. More precisely, the JEJ, because this does not depend on TT or non-TT. So the angular momentum loss in the center of mass frame, at order G to the 4, does not depend on this effect due to nonlinear. A lot to take in for the last 8 minutes. I hope we managed to get there. Any question? Everybody is eager to go grab a coffee or do something else in the nice weather.
Online
so yeah, online too as well. Okay, so one last thing, we were reminded exactly. So the next lecture is going to be on April 11th, which is Friday next week, on in the morning at 10, right? Yes. 10.
Yeah, usual time 10.
Okay, thanks a lot, and
Thank you.
see you next.